Hi everyone, Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad IZZAT bin Muhammad TARMIZI. My matric number is 8E230041. Today I will explain some technical problem with our homemade DC motor. So this type of motor is often used in a small device like electric toothbrush or remote control cars, but it has some limits. Okay, so first, it can overheat if used too long. So for second one, it is not very efficient because the design is simple. So the motor needs a better design to handle heavier work. So lastly, we must test its performance to make sure it can do certain tasks. So while the motor works, there is still a lot we can improvise. That's all from me.
Hi, Assalamualaikum. My name is Muhammad SHAFIQ bin Muhammad Yasin. My matric number AE230057. I will continue this presentation with project principle for the permanent magnet DC motor. Permanent magnet DC motor changes electrical energy into spinning motion, which is the mechanical motion. And PMDC, permanent magnet DC motor, use permanent magnet instead of coil to make a magnetic field. There's two types of PMDC motor, which is brush and brushless. And the parts of brush PMDC motor is the rotor and the stator, commutator and the brush. So how it's work? When the power is applied, the current will flows into the rotor and magnetic field interact, the rotor will spin and the commutator and brush keep changing current direction. This make the rotor spin non-stop until the power supply is cut, and the brush wear out over time, so it will lower the performance of the PMDC motor.
Okay, for next, I will explain our design planning for the homemade DC motor. So first, we wrap the copper wire tightly around a plastic syringe to make the coil. So then we insert a metal rod inside the syringe to help to increase the magnetic strength. So after that, we connected both end of the wire to a battery or power source to create current flow. So finally, we use screw and plastic caps to hold the coil in place and keep everything steady. This setup is simple but effective for small DC motor experiment.
So, Assalamualaikum warahmatullahi wabarakatuh. My name is AKASHAH bin RASHID and my matric number is AE2300N38. So, the next I will present about the description of design process. So, the first is the component selected. We are selected the copper wire, plastic shrink frame, metal screw, bottle cap, and steel rod. For the wire winding, we are tightly coiled around the structure for the strong magnetic induction. For the screw, guided and rescrew. The wire also act as the part of the magnetic core. For the steel rod, we are placed centrally to intensity of the magnetic field. So for the bottle cap, it functions as a base of stability or insulation. And the last is the manual assembly. We are confirmed by the screwdriver, reflecting hand-on precision and physics application.
For the model, we use Simuli model represents a permanent magnetic DC PMDC motor. For the electrical side, includes DC voltage sources, resistor 0.4 ohm and inductor 333 micro H. For the conversion, electrical circuit connected to an electromechanical converter to produce mechanical output. For the mechanical side, contains ID rotational motion sensor to measure speed and inertial block to simulate load. And for the simulation setup, we input voltage variety of 1 volt to 8 volt in 1 volt steps. For the calculation, RPM recorded at steady state for each voltage input. And for the analysis, voltage versus RPM table created and plotted to analyze speed response. Insulated copper coil is used for winding the electromagnetic coil. Plastic syringes serve as the base structure for coiling the wire. Metal screws is inserted along the cylinder to guide and secure the wire turns during coiling and acts as magnetic core. For the serrate placed at the core to strengthen the generated magnetic field. Plastic bottle cap used for structure support or insulation at one end of the coil. Manual scroll is used to tighten screws and assist in assembling the setup. For the description of assembly work, we inserted screws into a plastic syringe to secure the wire. We wound the copper wire around the syringe to form the coil. We wrapped additional wire around the central metal rod to strengthen the magnet. We attach a plastic bottle cap for extra support. We use a screwdriver to assemble everything manually, and the assembly was neat, careful, and hands-on.
For the testing and result part, first we will talk about the simple motor test setup. So we will connect the motor to the power supply, and then we will use a multimeter to check the value of voltage supplied to the motor, and then we will take a tachometer and we will check the speed of rotation of the shaft. So we will then increase the value of voltage slowly, step by step, and write down the value of speed each time the value of voltage is increased. Then we will make sure that the wire are safe and connected correctly to make sure that there is no fire hazard because of the spark that produced by the brush. And then we will start with the low voltage first and then increasingly up the value of voltage, and we will make sure to be careful with the moving part of the motor. So this test is very important so that we can see the performance of the motor in real life. So as you can see in the table at the right side of the slide, so for the DC voltage sources that are supplied in the motor, which is 1, the rotational speed in RPM is 95.4. And then if we increase the voltage supplied to 2, the RPM is 191. And if we increase it to 3, the value of RPM is 286.5. And then if we increase it into 4, it will become 382. And if you increase it into 5, the value is 477. And the maximum voltage that we test the motor is 8 volt, and the maximum rotational speed is 763.9 RPM.
For the design phase, we choose motor type based on voltage, current, speed, and torque needs. For the construction phase, we build the motor using the design plan. And for the wind copper wire, we attach the shaft and assemble the body. We pay attention to wire tightness and shaft alignment for good performance. For the performance testing, we test how fast the motor spins, how much current it uses, and its torque. We compare real result with theoretical values. And for the error analysis, we note difference caused by friction, wire resistance, or measurement mistakes. Power connection setup can also affect the result. And for the improvement, we use better materials, adjust winding, or improve part alignment if needed. For the conclusion, design phase, we selected motor step specifications, voltage, speed, torque, and calculated key values like back EMF, torque, power, and efficiency. For the construction phase, we built the motor using copper wire, a shaft, and other parts, focusing on neat and accurate assembly. And for the hands-on building, we deepen our understanding of how motor components work together. For the performance analysis, we test the motor speed, current use, and efficiency, comparing the result with our calculation. We identify errors such as tool inaccuracies, wire resistance, friction, and connection issues. The experience developed our problem-solving, precision, and critical thinking skills.
Hi, my name is MOHD NAJMI bermamat KHALID, matrix number AE230044. and I'm going to be explaining all of the appendix. So for the appendix A is picture shown of our prototype, which is the DC motor. For the appendix B, this shows the result from our simulation, which is from 1 volt to 8 volt in 1 volt increment. The graph here shows the RPM for each volt. For the appendix C, it shows the materials and its function that we use for the prototype design. In the appendix D, it shows the testing picture for our lab test. This is the live demonstration. It shows the voltage and the RPM that was recorded. This is the live. This is also the same. It shows that 6.0 volt, 6.07 volt is 625.29 RPM. This is also the same. It shows that 6.0 volt, 7.30 volts, and 143.64 RPM. 7.30 volts and 140 RPM. And the last one, 8.27 volt at the RPM of 1241. That's all for me. Thank you. RPM. And the last one,